Hi everybody, we're continuing Chapter 2 information on basic chemistry. In this PowerPoint, we're going to talk about inorganic compounds and the pH scale. In the course pack, you can follow me on pages 14 through 16. So you may have heard of the terms organic produce before, but organic produce and organic compounds have a bit of a different meaning. So when we talk about the word inorganic compounds, we are talking about chemical compounds that are usually ionically bonded together. These kinds of compounds also typically lack carbon and hydrogen atoms, and they may or may not be made by a living organism. And of course, these rules are made to be broken. We'll talk about some exceptions to these rules in just a moment. So here you can see on the left an inorganic compound which does lack the long chains of carbon and hydrogens, while on the right side you'll notice an organic compound with many carbons and hydrogens linked together. Just as a way of a great review, you'll notice the C stands for carbon, H for hydrogen, and those lines in between indicate what type of bond. Those are single covalent bonds. So let's talk about water, which is a wonderful example of an inorganic compound. Let's review the structure that you see here. Water is considered a polar covalent molecule, which means that the bond between the hydrogens and oxygen are not done in an equal sharing manner. In fact, oxygen takes more than its fair share of time with the electrons that it's sharing with each hydrogen atom. Because of that, we represent the unequal sharing by using these delta symbols here. Delta negative meaning the oxygen gets more than its fair share of negative electrons, and the delta positive over here means that hydrogens get a little less time with the electrons, and all they have is that single proton in the nucleus. So water is a polar covalent molecule. If we were to write it out, it would be HOH, or we can use this shorthand and just simply say it's H2O. Because water is a polar covalent molecule and oil is nonpolar, they do not mix together. We know that water or polar substances and nonpolar substances do not immerse or mix together. So in our bodies, 65% of a person's body is typically water, and when we're looking at water and oil, such as what's formed on the skin surface, those two don't get along together. So that's why water beads up on the skin surface. So we have to have a creative way for water to move throughout our bodies, considering that plasma membranes of cells are largely composed of a lipid like oil. You may also recall us talking earlier about hydrogen bonding. This type of bond occurs between adjacent water molecules. Let me circle a water molecule here and a neighboring one here. You'll notice the attraction between the hydrogen and neighboring oxygen creates a weak attraction that we refer to as a hydrogen bond. And in this picture, you can spot it because it's shown up as a dotted line. So you're only going to have hydrogen bonding between these polar molecules, between a slightly positively charged hydrogen and a neighboring slightly negatively charged oxygen. You can also have hydrogen bonding between hydrogens on water molecules and other types of electronegative molecules, such as fluorine, for instance. So it is the hydrogen bonds here that help to make these water molecules cohesive or stick together. Here you can see the play of cohesion and surface tension allows this insect, water strider, not to break the surface tension and fall through. So in our bodies, water molecules do tend to stick together, which means that blood flows through our vessels, for instance, or surrounds the outsides of many of our organs. Water is a great cushioning device in the body. It is found in the interior of our cells. This term is called intracellular fluid, and it may be abbreviated as ICF. This accounts for around 2/3 of the fluids in your body. That's about 25 liters of fluid in the intracellular space. The extracellular compartment, or ECF, is found outside of our cells, and that is mainly found in two places: blood plasma, which is the fluid in the bloodstream, and interstitial fluid, which is the fluid between cells outside the bloodstream. Now, there's other extracellular fluids. You'll learn about them, both Bio 210 and 211, but these two here, plasma and interstitial fluid, account for the majority of our extracellular fluids. Since intracellular fluid counts for about 2/3 of our bodily fluids, extracellular fluids only count for about 1/3 of our bodily fluids. Electrolytes are our next category of inorganic compounds. They are ionically bonded together and they will break apart, which means to dissociate, when they're dissolved in water. So ions can be classified as either cations or anions, and that's what happens when these electrolytes get into water. Under the electrolyte umbrella, we classify things like acids, bases, and salts. These are some common electrolytes that you should be familiar with. We will talk about these throughout this course and again in Bio 211. You will become very familiar with the functions of sodium and potassium in terms of regulating muscle and nerve function. We'll also talk in Bio 211 about bicarbonate acting as a buffer system to maintain your body's pH, as well as phosphate. So you may want to take a hard look at this list. If you're unfamiliar with the symbols of these elements, now is a good time to commit them to memory. So just a kind of a rundown here of the importance of each of these types of electrolytes. Potassium and sodium are both important for neuron and muscular function. You'll notice also that sodium helps to maintain fluid volume and balance. It's a major influencer for osmosis and the movement of fluids. Sodium and chlorine do work together to help maintain fluid balance in our bodies. And then, of course, magnesium also works in muscle function as well as sodium. We know a lot about calcium. We know that it's stored in our bones and our teeth, and it's also important for muscle and nerve functioning. Phosphates and bicarbonates, you'll notice here, important for tissue growth and repair, and also bicarbonate there helps to maintain proper acidity. Like I mentioned earlier, it's an important buffer in our bloodstream. So overall, we can classify electrolytes as being important for osmosis, which is water balance in the body, and hydration, and also for muscle and nerve physiology. That's two places we'll discuss it in both Bio 210 and 211. So let's talk about a subcategory of electrolytes, which are the salts. They are, of course, inorganic compounds. They are ionically bonded together. That means in water, they break apart into two components. What are they? They're cations and anions. You'll notice these salts, however, don't contain hydrogens here or hydroxides here. All right, so if they were to contain hydrogens, they would be considered acids. And if they had the hydroxides, we would consider them bases. So you'll notice in our three examples down below, there's no hydrogens or hydroxides listed there. Let's pick on sodium chloride, which is NaCl, for just a moment. We know that's table salt. And when it gets in water, it breaks apart into its components, a sodium ion and a chlorine ion. Which one of these is the cation? Well, it's the one with the positive charge, and that would be sodium. Chlorine carries a negative charge, so it would be the anion. So in this relationship here, in this ionic bond, which one of these received the electron during the transfer? That would be chlorine. Sodium gave away its electron. Let's talk now about acids and bases. We'll talk about them in reference to the pH scale that you can see here. We use this pH scale that runs on a scale from 0 at this end to 14 at this end. It is based on hydrogen ion concentration in solution. Right here, hydrogen ion concentration in solution. So the H in pH is actually hydrogen ion concentration. You'll notice it's a logarithm scale. Down here, you can see it's based on the number 10. Okay, so like right there's an example. And that means that every time we move a number on the pH scale, we move a 10-fold change in either acidity or alkalinity. That means that, for instance, if you drink a cup of coffee that has a pH of 6, it's actually 10 times stronger than a coffee with a pH of 5, and 100 times stronger than a coffee with a pH of 4, and 1,000 times stronger than a coffee with a pH of 3. And guess what? 10,000 times stronger than a coffee with a pH of 2. So when we're moving on the pH scale, we are basing it on the number 10, and we multiply times 10 every time we move from one number to another. Let me give you a shortcut way to figure this out as well. If we're trying to figure out the difference in acidity or alkalinity between a couple of numbers, you can simply say, well, the difference between the pH of 8 and the pH of 6 is 2, but put that as a superscript on the 10. If you're comfortable working with superscripts, you'll know that that means it's 100 times difference. So you can say 10 times 10 is a 100-fold change in acidity, or you can say it's 10 to the power of 2 times different in acidity or alkalinity. Let's also talk about the language here. If you're talking about 8 compared to 6, you can say that 8 is 100 times more alkaline than 6, or just reverse it. 6 is 100 times more acidic than 8. Let's also talk about what we release. 7 is the neutral number on the pH scale. Okay, that's 7.0. Below 7, these chemicals release more hydrogen ions. They're, of course, considered acids. The closer you get to 0, the more hydrogen ions that chemical releases, the more acidic that chemical is. As you head in the opposite direction, these chemicals to the right release hydroxide, sometimes referred to as hydroxyl, and these are known as bases. Okay, so the further you get away from 7 and closer you get to 14, you're looking at a stronger base. So let's go back to our example. A pH of 6 releases 100 times more hydrogen ions than 8, or you could simply say 8 releases 100 times less hydrogens than 6, or you could say that 8 releases 100 times more hydroxyl ions than 6. So let's do another example. Let's talk about the difference between 3 and 6. Okay? So how many times difference are they? What is the change in pH here? Well, we can use this shortcut. 10 to the power of 3, well, that's 3 zeros, right? Okay, so there's 1,000 times difference in the strengths of those two acids. Which one of those two is stronger, 3 or 6? 3 is the stronger of the two acids. You could say it releases 1,000 times more hydrogens than 6. Or you could say 6 releases 1,000 times less hydrogens than 3. Let's talk about some examples of acids in the human body. You're looking at a few great ones here. Stomach acid is one. Saliva is another. Female vaginal fluids. Okay, so those are 3 great examples to list on your worksheet. Let's talk about great examples of bases. Blood is a good example. Pancreatic fluids, and male semen. There's a couple of practice problems on the bottom of your worksheet for changes in pH. Do let me know if you have any questions about this. So on this slide, I would like to show you one thing here, and that is about this neutral number 7. Okay, we know that's 7.0. Not 7.1, not 6.9, but right at 7.0. And it looks like we're releasing equal amounts of hydrogens and hydroxides. Interesting thing about that, because right at 7, you do combine these two, and the only thing to be at neutral 7 is water, which ironically happens to be the hydrogens and hydroxyls released in equal amounts. So I just want to show you this picture to illustrate that the pH changes are on a continuum. It's not a hard line here at 7 where neutral is located, that you have all of a sudden hydrogens being released and then hydroxides being released as you cross that line. There's a continuum here. Some acids actually release a bit of hydroxide and some bases release a bit of hydrogens. So I want you to see that there is a scale or a range here that we're looking at. Okay, so the pH scale is a measure of hydrogen ions in concentration. It runs from 0 to 14. Your weakest are closest to the neutral number 7. Your strongest acids and bases are toward the ends. They're toward 0 and toward 14. Okay, so if you have any questions on pH scale, please let me know.